Good Wednesday evening.
Good evening.
We continue our study of random variables. We are studying only one type of continuous random variable.
For the or for the entire?
Not for the entire. The other ones are definitely way more complicated. Even this one's kind of complicated, but we have tables that make it easier. First, we look at a probability density curve. This represents the probability distribution of a continuous random variable. The area under this curve is equal to 1. The area under the curve between two values A and B has two interpretations. First is the proportion of the population whose values are between A and B. Two, it is the probability that a randomly selected individual will have a value between A and B. So discrete random variables dealt with sums. Right? Probability between A and B was a sum. For continuous, it's an area. And in math, area is an integral, which is calculus. Only density curve we study in this course. You're probably familiar with it. It's called the normal curve. That is its shape. This you're not going to need to know. All density curves have a density function. For the normal, Mu is the mean, sigma is the standard deviation. Domain is everything. It is a beast of a function to work with. But luckily for you, all of that work's been done already, so you don't have to worry about it. Properties of the normal distribution. It is symmetric about the mean. Mean, median, and mode are all the same. And this one's already mentioned, but total area under the curve is equal to 1. And so that shaded region is just 1. Because it's symmetric about the mean, if you draw a line at the mean, dividing that area perfectly in half, then your two areas are both equal and they're each 1/2. The empirical rule applies. I remember what the empirical rule was. This was way back. "68% of your data is going to fall within one standard deviation of the mean. That area is the area that is from the mean minus the standard deviation to the mean plus the standard deviation. And that area has to be 0.68. Within 2 standard deviations, you have about 95% of your data. So the area within 2 standard deviations of the mean would be 0.95. Oh, that's not right. I don't have that image anymore either. I'll have to fix that later. 0.997, so that should not be 97%, that should be 99.7%. So area within 3 standard deviations of the mean, 0.997. About. These are all actually just rough estimates. Right, that's not exactly 68%. I think it's like 67 and some change. For the 2, I think that's 95 and some change. there is a special type of normal distribution. We call it the standard normal. Standard normal is a normal distribution in which the mean is 0 and the standard deviation is 1. Whenever we're working with a normal random variable in this course, we will have to convert it to standard normal. This is called standardizing the distribution. And we do so by the use of z-scores, which again we studied earlier. And then we will be using a table, specifically table B, which is found on Blackboard. So it'll be cross-referencing this a lot. I highly encourage you to print this table out. If you don't have access to this table, most of what we're going to be doing is not going to be possible. How do you find the z-score for a data point x?
Minus the mean divided by the standard deviation.
That was measures of position, which is what, the second week? And then what you'll see is if we're talking about a standard normal distribution, would typically represent that random variable with a capital Z. And so then your standard normal distribution would be your set of all those ZX values. So Z is a random variable, it's a standard normal random variable. Find the value of Z corresponding to these probabilities. Am I going to draw or am I going to cheat? I think I'm going to cheat. Oops. That way I don't have to draw it myself.
Is that order?
Looks like about half right there. No, it doesn't. That.
Let's see if we can-
Ah, it looks more like half. Now remember, that is the mean, so that's 0. So we want the probability between 0 and some value z to be 0.4429. So let's call that value there as z. That's the value we're trying to find.
So what we're trying to find should be equivalent to that number that is up there before.
We're trying to find the value z that makes that area 0.4429. That is what we're looking for. So that's the z we have to determine. There's a problem though. The chart's only giving us an area for less than or equal to. But that's okay. Because what do we know about all of this area? That's 3.5. Which means if you take all of the area less than or equal to z, what is it?
So it's still that it always has to be 0.5.
Each side is always 1/2.
You just add those two.
Uh-huh.
0.942.
That's the value of little z that we're looking for. That makes the area 0.9429. Total area to the left. So you come over to the table. You want this page, because we're to the right of 0. So you want to look in the body for 0.9429.
Is it 1.500.8?
0.9439.
9429, right? 1.5 Z and 0.08.
Oh, you can also just highlight it. It's right there, right?
Mhm.
I have a question for that. We have to
1.5.
add the number 0.5 or we have to subtract?
Add for this one. Because we're looking for total area less than or equal to. Not want it to highlight like that. 1.58.
So it has to be like this, not like this.
It's both. 1.5 plus 0.08,
Okay, so
1.58. For part B, there's a Z. We're looking for that value that makes the total area to the left of it as 0.7967. Oh, and this one's easy. The table already gives us area to the left. So all we have to do is look for 0.7967. And again, we want this the second page because the z-score is to the right.
7967, 0.83.
0.7967.
Yeah, 0.83.
There's 0.7967. And I knew it was to the right because the probability was greater than 1/2. If it was less than 1/2, I'd be to the left of 0.
So, for that, the Z, we have to just get the estimate for the Z, or we just 0.79 is kind of the 80%, and then there's the Z is the 20%. We have to count like that.
Hmm?
For the graph, then you put the Z.
Uh-huh.
So for that one, is because of that number is a count like as 80% and then the 20% kind of. We have to, or we can put the Z.
So this is saying that the probability that you're less than or equal to Z is that 0.79. Right? Since it's less than or equal to, you're looking for area to the left of your Z value, which is why it was this side over here.
So how do we distinguish what are you looking for? Looking for it from the right or to the left?
By the sign.
Oh, by the
But, or, I don't want to say by the sign. By the inequality that you're given. Right? The inequality always points to the direction that the area is located.
Okay, so in another sense, the larger the number is, the closer.
So in this case, this is 0.7967,
Yeah.
which is greater than 1/2. So that tells you that your z-score has to be to the right of 0 because from 0 to the left is a half.
Okay.
Since we're larger than a half, there has to be some area to the right of 0. Between Z and 2 has an area of 0.1. Let's call that Z. Let's call that 2. So we want that area to be 0.1000. First, let's look for that. It shouldn't be too difficult. So come to the chart. We want a z-score of 2.00. It's that area.
I didn't understand how we got that.
Hmm?
I didn't understand how we got that part. How we got it.
Because I'm looking for less than or equal to 2. So that's 2.00. Right, so it's the 2.0 row, very first column.
Okay.
That's the area. To the left of 2. So before I change screen, leave that up there so I don't have to remember 0.9772. So we know that that's that probability.
And that will be the suspect.
This is what we need. That's the number we need to be able to read it from the chart, right? So that would be what? Just this bit, this all here, right?
Mhm.
Well, if we know that this total area is 0.9772, and we know what this area has to be, how do you find this area?
Subtract from
Yeah, he's tracking. So what is this probability?
Is that 8772?
That's the number we're looking for in the chart.
You can go with the 8770, right?
Not quite. Yeah, I guess in this case we'd have to. Right, there is no 0.8772. This is all we have. Generally speaking, if you're between two values, you're supposed to take the average. So 1.165 usually, but that would definitely not work because we're actually closer to 1.16. So maybe be something like 1.161. However, my answer sheet says 1.16, but they have a different table than this. So that's what I'm going to go with.
What if we don't have something to do with? And we are in such situation.
I would accept anything between those two values, 1.16 and 1.17. What's easy is 1.16. It's actually not. It's close enough for government work. So obviously that is going to be a limitation. Because the chart only goes up to 2 decimal places on the z-score. So that is a massive limitation. It'd be a lot easier to find it using calculus. These are kind of more of the same. Oh, just be about 0. Except now we're looking for actual probabilities. Right? So between 0 and 1.35, I could add 1, 2, and 3 on here if I wanted to. And of course, too much work. Let's just say there's 1.35. That is the area we're looking for. However, our table only gives us area to the left. What is all that area, though? So we can find that area easy enough. What are we going to have to do to it to find our desired area? Hmm? We already have the z-score, it's 1.35.
So we'll add it to the 0.5.
Add.
Add that, or multiply.
So if we look at area to the left of 1.35, that'd be that, wouldn't it? The yellow. How do you get the white from the yellow?
You take that, remove it, erase it.
You subtract 1.35 from 0.5.
Not 1.35.
0.5.
Whatever that area happens to be, 1.5. Or 0.5 from that yellow area.
So like 0.5 minus 1.5.
That represents the yellow area. Subtract from that the 0.5, right? That'll give you what's left in the middle, the white. Because we can find that area in the chart, can't we? Less than or equal to 1.35.
I see what you're saying.
So where's 1.35?
That's 1.3.
Right here.
So it's 1.3.
So that total yellow area is 0.9115. So all of this is 0.9115. We just want this bit. Well, that is everything minus what's to the left of 0, right? And to the left of 0 is 0.5. So there's your area. There's your probability, 0.4115. Between negative 1.21 and 0, I don't know, negative 1.21, right about there.
Or we can check value from the table and minus.
Hmm?
We have to check value from the table from 1.21.
Well, that's not going to give us what we want. because that's what we want, right? But we know 2 value. Well, we can easily find that value. Right, that yellow is just that probability, right?
0.1131.
Yeah, so it's that area, 0.1131. Right? But how can we get the white area from that? We also know that, don't we? What's that? Isn't the shaded white everything to the left of 0 minus everything to the left of negative 1.21?
I think I know.
Is it 1?
0.5 minus 1.1.
Right, because that middle shaded region is everything to the left of 0. Right, that's all of this minus what's to the right of negative 1.21. What, 0.4869?
I got 3869.
Oh, yeah, it is 3. I ignored that first one. There's your probability.
I'm a bit confused. I understand it, 0.5, did you just add the 3 zeros, or that was a figure?
I added the 3 zeros just to have the same number of decimal places.
Okay.
Right, 0.5 and 0.5000 are the same thing.
Yep. Okay.
You don't have to do that, typically wouldn't. But since we're just doing this for the first time, I added the zeros to make it easier. Now we're looking for the probability that z equals 1.5. There's 1.5. What area are you looking for?
Look for the chart. For 1.5 or 50.
Well, that gives you the area to the left of 1.5. Is that what the probability is asking for?
And it's like the right side of
If I'm looking to the right, what would the inequality be? Is that greater than or equal to?
Just still 1.5 in the chart.
Again, that only gives you area to the left. Equals 1.5 is just that line, isn't it? Does a line have area? This probability is 0.
Now on a test, we would have to write that if the equation comes up like that.
Yeah, it's just 0.
Is right.
Now, in actual fact, the probability is not 0. It is just an extremely small number. So small that we call it 0. Let's call that 0. Probability that z is between negative 1.37 and 1.35. So, I don't know. Maybe negative 1.37 is there. Maybe 1.35 is there. It's just a sketch. Right, not drawing the scale. That's what we're looking for, right? That probability gives us everything to the left of 1.35, right? And that probability would be everything to the left of negative 1.37. Our desired area would just be their difference. And we can find both of those areas from the chart. So let's get rid of that. Let's first look for 1.35. 1.35 right here. So 0.9115. Yes?
Minus 160 is 0.
And it was negative 1.3.
0.085.
37. There's negative 1.3. 0, 1, 2, 3, 4, 5, 6, 7. Point 0853. I am too lazy to do that in my head. Good thing I brought my super calculator. That is super overkill for this problem. Here's your probability.
Yeah.
See that? So notice all these problems have literally been just reading from the chart. And a little bit of graphical interpretation. Between 0.65 and 1.26. That's not getting any room there, though. That's the problem. Oh boy. I'm going to get rid of that 0 there then. That's what we're looking for, right? Keep in mind you don't actually have to draw a picture every time. It just helps you to visualize it. It's going to be everything to the left of 1.26, right? Minus everything to the left of 0.65. So looking for 0.65. That would be the area. Oops. Sorry, I drew it on the wrong one. 7.442 there. 1.26.
8962.
This one here. Yeah, 0.1520. They did not change that clock. Man, I'm thinking it's been 2 freaking hours already. I'm like, there's no way. Damn, you're giving me a heart attack.
Sir?
Hmm?
0.65. That value is 7422. We put 7442.
Glad you saw that. That's for that.
So this should go up to 4 instead of 2 then.
154.
Yeah, 0.1540. Between negative 1.79 and negative 0.54. It should be no surprise that's a difference. All right, our z-scores are negative. First page. Negative 0.54.
4946.
Yeah, here, 0, 1, 2, 3, 4. So it's that one. Why can I see more on my screen than there? What was it? 2946? And then minus 1 point, or negative 1.79,
0.0.
which is all the way over here, right? 0.0367.
2579 also.
What'd you say it was?
2579. 0.2579.
Easy, right?
No, it's not.
Not in the exam.
Not easy?
Here is easy.
Maybe the easiest thing we've done all semester. Maybe.
Up there is where the trick is. Not getting this. When you understand that, I guess you're gonna get this easy.
Well, good news is whenever your z-score is between two values, it's always the difference of the larger and the smaller. And so if you remember that, you're golden.
Trick is smarter from the back.
Oh, no. So we're going to have to go back. Oh, for Pete's sake. Oh, why do you make everything so difficult, PowerPoint? Let's say right there's our 0, right? Less than negative 0.22. Well, that would be what? That area, right? Oh. Oh. Oh, that's nice. The chart gives us that right off the bat, doesn't it? Oh, that's nice. So it's what, negative 0.22?
Yeah.
So negative 0.2, 0, 1,
412.
2.
The first one is always 0.
Yes. Right, it's going to be easier when you have it printed out because you actually have the column headings on screen as well. Don't have to worry about scrolling all the way up. So that's our answer, 0.4129. So If only everything in life was that easy. Less than or equal to 0.33. Of course, it's pop up. Server's too busy to upload. Go away. That pop-up made me color outside the line. That's what we're looking for, right? Once again, that can be read directly from the chart.
6293.
Right there, right? Greater than or equal to 0.44. Since we're now looking at greater than or equal to, that's the area we're looking for, isn't it? Oh dear. That's not what our chart gives us. It'll give us this. So how can we get that from what we know here? Because we know the whole thing is 1.
Yeah.
So it's that. So it's 1 minus that area, right? That's all there is.
1 minus
1 minus
0.6700.
Now, technically, this is not correct. Technically, that's what we're looking for. It makes 0 difference when reading the table. You are not freezing because it's 70 degrees in here. Freezing is 32. Freezing is 32 degrees Fahrenheit.
It's really,
And even then, you wouldn't be freezing because your body temperature wouldn't go down that low. You would die long before freezing.
yeah, I'm cold.
What is the body temperature that would actually kill you? Isn't it like 90?
What, that?
No, what your body temperature, the lowest your body temperature can reach before death. It's not that low.
Pretty close to it.
I think at
No,
90
yeah.
it's hyperthermia or something like that. So you would actually never be freezing because you'd be dead long before that.
You're gonna start cutting vitamins right now.
So I'm just being completely literal. You're not freezing.
You're never cool, but we always cool.
I spent 10 years working in an industrial freezer that was 40 below.
You didn't come out of there with pneumonia? You didn't walk out with pneumonia?
By year 3, I was going in there without a coat.
Really? So you don't get cold? It's cold.
If I get cold, then it's one of two possibilities. I'm either really sick, or it's just that damn cold out.
It's cold in here.
This is comfortable. If it was up to me, the house would be at 50 degrees.
If you have the blisters, just save us.
We're looking for 0.44.
6700.
That's right here. Well, we're doing some thinking, so it should be warming you up. Math warms you up. It's good for the soul. Another easy way to warm up is if you're 21 or older. A few shots of Jack. Warm you right up. I know that from experience. That is 0.3300. There's your probability. Greater than or equal to negative 0.55. How are we going to find it?
Same thing that we did last time.
Which is what?
1 minus
To 1 minus the.
0.5.
Was not in
Probability what?
Means it's worse than that.
Less than negative 0.55, right?
So how would that out?
Right. Again, we are left at 0, so we're up on this first page. 0, 1, 2, 3, 4, 5. 0.2912. Which is 0.7088. Right? So that's working with the standard normal distribution. Questions there? That means next one will be working with problems where it's not standard normal. It's just normal.
Oh, this is standard normal.
All that we just did was z's, which are standard normal. Now we're actually going to have to standardize before we can do this. So just one extra step. Yeah, one extra step. may have to calculate two z values, depending on if it's between two values or not. But let's pick 10. So we'll come back at 35.
Always do. Yeah, when I was outside, that's what myself is. Tasty, whenever I see your name, I'm gonna respect it. Whenever I see your name, it's that tasty, I run for my life. I run up my life, and then I don't need to. Those 10 minutes.
Alright, so this is just repeating what we already saw, z-score. So remember, z is x minus mu over sigma. So let's suppose IQ score form a normal distribution with mean of 100. Find percentage of students whose scores fall between, so start with between 80 and 120. The first thing we have to do is convert them to z-scores. $80 minus the mean over the standard deviation. Negative 1.00, right? And z of 120. 120 minus mean over standard deviation. 1.00. The probability that we're looking for, that x is between 80 and 120, is the same as the probability of z being between -1 and +1. Number was excluded from my block. And we know how to do that. From what we did previously, that's that difference, right? Now it's just back to the chart. I'm already here, so negative 1.00, 0.1587. You see that? And then 1.00, 0.8413. Point 6826, which matches up with what we would expect from the empirical rule. About 68% of data falls within one standard deviation of the mean, which means about 68% of your data is going to be between negative 1.00 and 1.00 for a standard normal. So that matches up. Between 60 and 140. Again, we need to convert these to standard units. That is negative 2.00, right? On 40 minus mean divided by standard deviation, which is 2.00. All right, so the probability we're looking for is the probability that z is between -2 and +2. What does the empirical rule tell us this probability should be, approximately? So, right around 0.95. Again, it's not going to be exactly 0.95. That's the difference we're looking for based on our chart. (2.00) 0.9772. Negative 2.00, 0.0228. .9544. Which is about 95%. Between 40 and 160. Again, we have to convert those two values to z-scores. $40 is negative 3.00. 160 is 3.00. So we're looking for the area between negative 3 and positive 3. .9987 would be for less than 3.00, right? Minus,
0.0013.
now we want negative 3.0, 0.0013. That would be what? 0.9974? Which again matches with the empirical rule. 99.7% approximately. Now between 100 and 120. Well, what would the z-score for 100 be? It has to be 0 because 100 is the mean. And it's standard, normal, mean is 0. Oh, by the way, we did 120 already. That was 1.00. Isn't that just half of that area? So there's no need to do any work using symmetry. Because it's perfectly symmetrical about 0. You wouldn't be able to use symmetry if that was not 0. But it is 0, so we can use symmetry. So it's going to be half of 0.6826. I shouldn't need to do this. It's what, 0.3413? So if you can, take advantage of symmetry. What did we say the z-score for 160 was?
Three.
We're looking for over 160. Oops. So we're looking for the probability that z is larger than 3. That, right? 1 minus the probability that we're less than or equal to 3. Oh, but we did that already. It's 0.9987. Oh, which means we could just use symmetry again and say that that probability is the same as this probability. So I'm actually going to do that instead of the 1 minus. By symmetry.
And you thought it was just like that, or you have to continue on?
Well, I started to continue on. Right, so instead of doing 1 minus the probability of z less than 3, I can just look in the chart for less than negative 3.00. But we did do that. We already saw that. It was 0.0013. Right, because we have to find it here. Less than 80. What was the z-score for 80? So the probability that x is less than 80 is the same as the probability of z being less than 1.00. I think we found that one too already. That was up here, wasn't it? 0.8413. So I don't need to go back in the chart for that because we just did it. Oh, wait a minute. 80 is -1. Sorry, not +1. So it's not that one. It is 0.1587, this one here.
It would still be positive.
Probability is always positive. It's always between 0 and 1. So, like I said, just one additional step we have to do, right? You have to first now convert your values to z-scores. Then you can go to the chart. So let's suppose the temperature during May is normally distributed with a mean of 68 degrees and a standard deviation of 6 degrees. Find the probability that the temperature during May is between 70 and 80 and then less than 60. So Z of 70. Minus mean over standard deviation. Go back to 3 decimals, because that's what's in the chart. Is it?
Yeah.
No, it's 2 decimals in the chart. You're right. And then of 80 minus the mean divided by standard deviation. Probability 70 is less than or equal to t, less than or equal to 80 is the same as the probability that z is between 0.33 and 2. So we need the probability of less than or equal to 2, which we did get previously. 0.9772. Right. Minus the probability that z is less than or equal to 0.33. Which is right there, 0.6293. Point 3479. Less than 60. Minus the mean divided by standard deviation. So it's -8 divided by 6. What was it? -1.33. That's what we're looking for, which can come right from the chart. So let's look for -1.33. -1.3, 0, 1, 2, 3, 0.0918. Let's just make sure I have enough time for everything. you do that on your own.
We don't have to check.
Right? Process is the same. Convert to z-scores first, then interpret the area from the chart.
Change the slides.
Hmm?
The slide changed.
I know. So you can do that on your own. Means outside of class.
Oh, okay, okay. Okay. At least we already did this.
So sample mean distribution. Now what we're going to do is really delve into inferential statistics.
Okay.
And the first thing we want to study is how is a sample mean distributed. This is going to lead us into what's known as confidence intervals, which we look at next week, which will ultimately lead into hypothesis testing, which is all of inferential statistics. Sampling error. Error resulting from using a sample to estimate a population characteristic. Right? You're obviously not going to be able to perfectly estimate something about a population just from a sample, no matter how good your sample is. Variable x with a given sample size n, the distribution of all possible sample means of size n, which we represent as x bar, is called the sampling distribution of the sample mean, or just the distribution of the sample mean. The larger your sample size, the smaller the sampling error tends to be. So how is it distributed? You have two broad cases. First, if your sample is already normally distributed, then your sample means will be normally distributed as well. The sample will be guaranteed to be normally distributed if your population is normally distributed. That's actually not true, I lied. That could pick it so it's not normally distributed. So if you already know that your sample is normally distributed, you're nice. You're done. Your sample means will be normally distributed. And then we can use the process that we just learned. The other case is your sample isn't normally distributed. This is where the most important theorem in all of statistics comes in. It's called the central limit theorem. Which states that for a relatively large sample size, say n is greater than or equal to 30, x bar is approximately normally distributed regardless of the distribution of the variable under consideration. Now obviously this approximation becomes better as n gets larger. Which leads to case number 2. If your sample size is at least 30, then x bar is approximately normal. Which means we can treat it as normal. And thus use the methods that we just learned. The final case is your sample size is less than 30. If x is not normally distributed, then x bar cannot be approximated as a normal distribution. And so we cannot examine it using the methods of this course. I think stat 2 goes into it. It's sampling theory, specifically small sample theory. I think that's stat 2. So in case 1 or case 2, the mean of your means is the population mean. The standard deviation of your means is the population standard deviation divided by the square root of sample size. And the standard deviation is sometimes referred to as the standard error. So let's say population consists of 5 numbers, 2, 3, 6, 8, and 11. First, find the mean and standard deviation of the population. Then we'll find mean and standard deviation of those 2 distributions. I'm assuming that we're assuming this population is normally distributed. No, we're not. Oh dear. Oh, that's going to be hideous. Let's start. Notebook. Let's call that pop. This is Excel. Finding the average for this population isn't too difficult to do by hand. Right, just add them up and divide by 5. This might be a bit of a problem. So I'm going to use Excel. And let's go to 3 decimal places. So 3.29. Alright, so I'm just going to write those at the top. All possible samples of size 2 that can be drawn with replacement. And we're looking for the means, obviously. Sample means. So if it's with replacement, sample size 2, how many means are we going to have? It's going to be 25 of them. Two with 2, 2 with 3, 2 with 6, 2 with 8, 2 with 11, 3 with 2, 3 with 3, 3 with 6, 3 with 8, 3 with 11, 6 with 2, 6 with 3, 6 with 6, 6 with 8, 6 with 11, 8 with 2, 8 with 3, 8 with 6, 8 with 8, 8 with 11, and then 11 with 2, 11 with 3, 11 with 6, 11 with 8, and 11 with 11.
So how you doing that?
Pick 2 numbers with replacement.
Okay, 2 number replacement.
So your sample size is, well, not your sample size, your sample space is 25.
So when you pick the one, you do your audit man or?
Finding the mean. So you pick your sample size of 2, find the mean.
Oh,
Right, and you're going to do that for every possible sample of size 2. And then you want to find the mean of those means. That's annoying.
I see. Two and two, two and three, two and six, two and eight, two and eight. One, three, one, two, two, three, three, two, eight, three, six, three, six.
Right, so mean of 2 and 2 is 2, 2 and 3, 2.5. 2 and 6 is 4. 2 and 8 is 5. 2 and 11, 13 halves, so 6 and a half.
Okay. You said two and two, right?
3 and 2, 2 and a half. 3 with 3 is 3. 4 and a half. 5 and a half and 7. Then it's 4, 4 and a half, 6, 7, 8 and a half. Now you're just picking your two numbers, adding and dividing by 2. That's the mean.
So that one is just for two, right?
5 point. No, the first 5 for 2.
The first five?
Yeah.
Oh, I think the first five for two.
Five. 5, 9.5, and 10.
I better write that down.
There's X bar. Now we get to find the mean and the standard deviation. So let me enter these into Excel real quick. average, samp mean replace. Did it not change it? It didn't. Mean is 6. Okay, cool. Oh, I see what I spelled it wrong. And standard deviation is 2.37. So that does not look like it's 3.28 divided by 5. Oh, I'm sorry, divided by root 2. Actually, it might be. 3.29 divided by root 2 is, no, it's not. It's 2.32, which means this is not normal. Now, all possible samples of size 2 without replacement. This one is much smaller. Two 3, 2 6, 2 8, 2 11, 3 6, 3 8, 3 11, 6 8, 6 11, and then 8 11. Because you're not replacing.
I don't understand that. So maybe if we go back to how we did it first, we're gonna get.
Well, I'm doing the same thing, except now I'm not replacing the value.
So,
Right? So I pick 2.
uh-huh.
What can I pick after 2? 3, 6, 8, or 11. I'm not replacing 2.
Okay. So when you do
So if you get 3, 6, 8, or 11, I'm not replacing 3. 6, 8, 11. I'm not replacing 6. You're left with 8 or 11. Those are all sample sizes 2 without replacement. So find their means. Those are all the means. Oh, I forgot to change the screen.
Last one.
All right, so again, I have them in Excel already. What am I going to name this? Let's name this samp mean. Now, Once again, mean is still 6. Standard deviation sample. And 2.12. So glad that problem is done. Right, but that is the distribution of sample means of size n. That's how you do it. Which means, by the way, if I would have said samples of size 3 with replacement, that's 5 cubed possibilities. 5 cubed is 125. So you'd have a distribution with 125 means in it. Have fun. Without replacement's better. So that's 5 choose 3. Which is 10. Yeah, it's 10. Assume that heights of 3,000 male students at a university are normally distributed with a mean of 68 inches and a standard deviation of 3 inches. If 80 samples consisting of 25 students each are obtained, what would be the expected mean and apparently standard deviation? It's okay, I don't need to know how to spell. Standard deviation of the resulting sampling distribution of means. And how many samples would you expect to find in the mean between 66.8 and 68.3 inches and less than 66.4? First, start with the mean. How many samples? Actually, it's just a sample size, right? What's the sample size?
Sample size would be 1,000.
0.5 students.
25. That's less than 30. Oh, but wait. Our population is normally distributed. So it doesn't matter what our sample size is. Means the mean of the means is the mean of the population. Standard deviation of the means. Standard deviation of the population divided by the square root of the sample size. Three over 5 is 0.60. stick with 1 decimal place, though. No, I'm not. 2 sig figs. Percent of the volume. That answers the first 2 questions. Now we can find probabilities. We were first asked between 66.8 and 68.3. That's what we're looking for. But we know that X bar is normal. Convert these to z-scores. (66.8) is negative 2.00.
What did you do?
Z-squared. 66.8 minus the mean divided by the standard deviation. And 68.3 is a z-score of 0.50. That's the probability we're looking for. So we go to the chart. (0.50), 0.6915. Less than or equal to negative 2.00, 0.228. Which is what, 6687? But what were we asked? How many of the samples would you expect to find the mean between those 2 values? Or how many samples did we take? No, that's the sample size.
Oh.
How many samples did we take? 80. So multiply that probability by 80, and that would be how many we would expect. How many of the samples we would expect. So let's say number of samples. We'll take that to be 53 samples. 53 or 54 samples. less than 66.4. So convert 66.4 to a z-score. What do you got? We'll say negative 2.67. Go back to the chart. 0.0038. All right, so the number of samples we would expect is that probability times 80. Which is 0.304. So we'd expect none of them to have a mean less than 66.4.
So after getting a 0.304, how did we derive at the zero the next zero?
Round it.
Round it?
Round it down. Because you can't have a fraction of a sample. Right? You can only have a whole number of samples. So I'm rounding it to the nearest integer. Which in this case would round down to 0. Or 1 if you wanted to round it up.
Yeah, so I saw the first one was 58. I didn't know how we got it 58.
It's 53, right?
50, yeah, 53.
Yeah, we just rounded it to the nearest whole number.
Oh, okay.
So 53 or 54. This would be like 0 or 1.
Okay.
What's the sample size here? 100. Is that larger than 30? Which means we can approximate this distribution as normal. Which means the mean of the means would be 5.02 grams. Standard deviation of the means. 0.30 grams divided by root 100, which is 10. 0.30 divided by 10, 0.03. Yeah. Then you would do this problem the exact same way we did the previous problem. Right, convert your values to z-scores, find the probability from the chart, and then multiply by 100. So quiz 8 will be due next week, and that's all on this stuff. Normal distributions and sample mean distribution.